Foundations of Quantum Computing. Quote, "The beginning is always today." Mary Shelley. Welcome to Chapter 1 of our journey into the fascinating world of quantum computing. In this chapter, we'll lay down the essential groundwork you need to understand quantum computing concepts and set the stage for the quantum algorithms we'll explore later in the book. Don't be daunted by the reputation of quantum math. We're here to show you that it's not as arcane as it seems. We'll begin with an overview of quantum computing, its current state, and its potential applications. Then, we'll dive into the most popular computational model for quantum computing, the quantum circuit model. This model will be our main focus throughout the book. We'll learn about qubits, the building blocks of quantum computing, how quantum gates operate on qubits, and how measurements extract information from qubits. Here's a preview of the topics we'll cover in this chapter. Quantum computing, the big picture. We'll start by discussing a groundbreaking event in 2019 when Google demonstrated quantum computational advantage. This milestone sparked worldwide interest in quantum computing's potential. We'll explore how quantum computing leverages quantum properties to achieve remarkable speed-ups in specific tasks. The basics of the quantum circuit model. This section introduces the quantum circuit model, which we'll use extensively. Just as classical circuits Python copy code def read or default, file path default, try, with open file path, as f, return f.read, except file not found error, return default. Exception. Chaining and wrapping Python allows exceptions to be wrapped or chained together. This means that when an exception occurs during exception handling, the original exception is preserved, and a new one can be raised along with the original context. Python's error messages provide details from both the original exception and the intervening one. By using the raise from statement, you can control the display of these chained exceptions. For example, when one exception occurs during the handling of another, Python copy code, try, 10 except 0 division error, 1 plus x, Python displays both exceptions. Arduino copy code, traceback, most recent call last, file, line 1 in 0 division error, division by 0. During handling of the above exception, another exception occurred. Traceback, most recent call last, file. Line 3 in type error, unsupported operand types for plus, int, and str custom exception classes. Python allows you to create your own exception classes by extending standard exception classes. This practice enables you to define your own exceptions with specific meanings for your applications. Custom exceptions enhance code readability and help distinguish different error scenarios. Python, copy code class, invalid attribute error, used to indicate attributes that could never be valid. Using custom exception classes allows you to handle specific error cases more effectively. You can catch these exceptions separately, which makes your code clearer and more maintainable. Error checking strategies, LBYL versus EAFP. Python promotes the easier to ask forgiveness than permission. EAFP error handling strategy over the look before you leap, LBYL strategy. EAFP encourages you to attempt an operation and handle exceptions that may arise, rather than checking conditions beforehand. EAFP is more readable and avoids duplicating code, making your program more robust and less prone to errors. However, care must be taken not to catch too broad a range of exceptions, potentially hiding unexpected issues. Logging errors and exception reporting. Python provides ways to handle unhandled exceptions and report errors. You can redirect error messages to a custom stream by rebinding sys.stdr. Additionally, you can customize exception reporting by assigning your own function to sys.acceptHook, which gets called when the program terminates due to an unhandled exception. This function can format and direct exception information for analysis and debugging purposes. Conclusion. In this lecture, we explored various aspects of exceptions in Python. We discussed how OS-error subclasses can streamline error handling, the concept of exception chaining and wrapping, creating custom exception classes for more expressive error handling, and the strategies of LBYL and EAFP for error checking. We also touched on error logging and exception reporting to enhance debugging and diagnosis. Exception handling is a crucial aspect of writing reliable and maintainable Python code. Handling multiple exceptions. Exception group and except asterisk. Python 3.11 introduced a mechanism to raise and handle multiple exceptions at once using the exception group class and the except asterisk form. This is particularly useful when validating data against multiple criteria, 1-qubit quantum gates and the block sphere. Good day, everyone. Today, we're delving into the fascinating world of quantum gates and the block sphere. We'll explore how 1-qubit quantum gates work, how they relate to rotations on the block sphere, and why these concepts are crucial for understanding quantum computing. So let's dive right in. 1. Qubit quantum gates. In the realm of quantum computing, a qubit is the fundamental unit of information. We've already learned how qubits store information and how to access it through measurements. But to harness the power of quantum computing, we need to manipulate qubit states for computations. This is where quantum gates come in. Quantum gates are analogous to operations in classical digital circuits. However, in the quantum realm, gates are represented by unitary matrices, ensuring that they preserve the length of qubit vectors, norm 1. The identity matrix and Pauli matrices, X, Y, Z, are fundamental gates. The X gate, also known as the NOT gate, flips the state of a qubit. The Hadamard, H gate, on the other hand, creates superposition, allowing qubits to exist in multiple states simultaneously. 2. The block sphere, visualizing qubit states. Imagine representing all possible qubit states on a two-dimensional sphere. This ingenious visualization is known as the block sphere. Each point on the sphere corresponds to a unique qubit state. For simplicity, we can use two angles, theta and phi, to pinpoint a qubit's location on the sphere. This representation helps us understand the effect of quantum gates as rotations. 3. Quantum gates as rotations. Here's where it gets truly intriguing. Quantum gates can be understood as rotations in the block sphere. For example, the X gate corresponds to a p-radian rotation around the X-axis, flipping the qubit's state. Similarly, Y and Z gates correspond to rotations around their respective axes. 4. Universal quantum gates. We're not limited to just X, Y, and Z gates. We can create any one qubit gate using combinations of rotations. This is a significant result in quantum computing. Moreover, some architectures use a universal gate called the U gate. It's a versatile gate that depends on three angles and can simulate any other one qubit gate. 5. Applications and significance. Understanding one qubit gates and the block sphere is essential for building more complex quantum circuits, designing quantum algorithms, and simulating quantum processes. They also form the foundation for controlled gates, which enable interactions between qubits, the quantum state, and unitary transformations. To set the stage, let's revisit the quantum state and its manipulation through unitary transformations. Quantum mechanics governs the evolution of a quantum state using the Schrödinger equation. We focus on unitary matrices, which ensure the preservation of quantum state norms. This is essential to maintain the probability interpretation of measurements. 2. Pauli matrices and quantum gates. We're already acquainted with the X, Y, and Z gates, represented by Pauli matrices. These gates have classical analogs, X, NOT, Y, a combination of X and Z phase flip. The Hadamard gate, H, deserves special attention. Its matrix elegantly combines the classical bits of information in a quantum superposition, enabling quantum parallelism. 3. The block sphere, more than a visual aid. The block sphere is more than a visual tool. It's a geometric representation of qubit states. A quantum state, PS, equal sign of vertical bar 0 plus B vertical bar 1, can be uniquely described using two angles, theta and phi. This geometrical representation reveals orthogonality, antipodal symmetry, and relationships between quantum gates and rotations. 4. Quantum gates as rotations. The connection deepens. Delving further, we uncover the profound connection between quantum gates and rotations. Any one qubit gate can be expressed as a rotation in the block sphere's three-dimensional space. For example, the H gate corresponds to a p-rotation around a specific axis. This connection underscores the geometric nature of quantum computation. 5. The universal U gate and quantum computation. The universal U gate's significance lies in its capability to simulate any other one qubit gate. By parameterizing rotations using three angles, we gain a universal tool for quantum computation. This concept bridges the gap between mathematical formalism and practical implementation, empowering us to create complex quantum algorithms. 6. Applications and limitations. The knowledge of one qubit gates and the block sphere forms the foundation of quantum computing. From quantum error correction to quantum simulations and cryptography, these concepts shape the field's future. However, it's essential to recognize that quantum gates alone cannot solve all problems. They are part of a larger toolbox that requires careful orchestration. Exploring two-qubit quantum gates and entanglement. Greetings, quantum explorers. We've embarked on a journey into the realm of two-qubit quantum systems, where new possibilities and mysteries await. In this session, we will delve into two-qubit states, quantum gates, and one of the most fascinating phenomena in the quantum world, entanglement. 1. Two-qubit states, building the foundation. As we transition from solitary qubits to two-qubit systems, we encounter a richer landscape of possibilities. In the computational basis, 2 qubits can exist in 4 states. 0, 0, $100, 0, 1, 01, a 10, 10, and child 11, 11, each representing a unique combination of individual qubit states. A general state of a 2-qubit system is a linear combination of these basis states. For instance, a 2-qubit state, Ps, can be expressed as equal sign 0, 0, 0, 0, plus 0, 1, 0, 1, plus 10, 10, plus 11, 11, Ps, a 0, 0, $100, plus a 0, 1, 0, 1, plus a 10, bird 10, plus a 11, number 11, here, 0, 0, a 0, 0, 0, 1, a 0, 1, 10, a 10, and 11, a 11 are complex amplitudes that must satisfy the normalization condition. Equal sign 0, 1, 2 equal sign 1 x, y equal sign 0, 1, a x, y, 2 equal sign 1, 2. 2-qubit gates, a new paradigm. In the realm of 2-qubit gates, we explore operations that extend beyond acting on individual qubits. These gates are 4x4 unitary matrices that can transform the joint state of 2 qubits. One way to construct such gates is by taking the tensor product of 2 1-qubit gates. The tensor product of unitary matrices 1U1 and 2U2 gives us a new gate 12U1U2 that acts on the combined state of 2 qubits. A circuit example involving tensor products would be circuit X circuit HI3, the Qiskit gate, control and entanglement. However, not all 2-qubit gates can be expressed as tensor products of 1-qubit gates. The controlled NOT Qiskit gate is a prime example. Its unitary matrix is 100001000100010, 10000100010, 1000010001010 in the Qiskit gate. The second qubit state is flipped if and only if the first qubit state is R11, introducing a form of controlled operation. This gate is pivotal in creating entanglement, a phenomenon where 2 qubits become correlated in a manner that classical systems cannot replicate. 4. Entanglement. The quantum magic entanglement is a cornerstone of quantum mechanics that defies classical intuition. When 2 qubits become entangled, their individual states lose meaning, and only their joint state carries significance. Measurement on 1 qubit instantaneously determines the state of the other, regardless of distance, a phenomenon famously described as spooky action at a distance by Einstein, Podolsky, and Rosen. The Qiskit gate plays a crucial role in generating entanglement. Applying a Qiskit gate to 2 qubits in the state 0, 0, 100, or 11, 11, creates an entangled state known as the Bell state. In conclusion, as we conclude this session on 2-qubit quantum gates and the captivating concept of entanglement, remember that the realm of quantum computing continually challenges our classical understanding of the universe. The ability to manipulate and study entanglement opens doors to quantum communication, quantum cryptography, and the potential for exponential computational speedup. In our next adventure, we'll immerse ourselves deeper into multi-qubit systems, exploring advanced topics like quantum gates acting on multiple qubits, the concept of quantum parallelism, and more mind-bending properties of the quantum world. Until then, keep embracing the quantum wonders that lie ahead. Multi-qubit quantum gates and beyond. Welcome back, curious minds. In our ongoing exploration of the quantum universe, we're about to venture into the world of multi-qubit quantum gates, quantum parallelism, and the enigmatic concept of quantum superposition. Let's dive right in. 1. Multi-qubit quantum gates, beyond the basics. As we ascend to more complex quantum systems, we encounter multi-qubit gates that can manipulate multiple qubits simultaneously. These gates are essential for harnessing the true power of quantum computing. One notable example is the Toffoli gate, a 3-qubit gate that acts as a controlled NOT gate. The Toffoli gate operates in a manner where the target qubit state is flipped if and only if both control qubits are in the state 1. It plays a pivotal role in constructing universal quantum computers, allowing the execution of any quantum computation. 2. Quantum parallelism, simultaneous computations. Quantum parallelism is a fundamental concept that sets quantum computing apart from classical computing. In classical computing, each bit has a single value, 0 or 1, limiting computations to a linear sequence. Entanglement, no cloning theorem, and controlled gates in quantum computing. Greetings, fellow explorers of the quantum realm. In this lecture, we're about to unravel the mysteries of entanglement, delve into the intriguing concept of the no cloning theorem, and master the construction of controlled gates in quantum computing. So, let's embark on this intellectual journey together. 1. Entanglement, defying classical intuition. Prepare to have your classical intuition challenged. The concept of entanglement is at the heart of quantum weirdness, but before we define entanglement, let's establish what it's not. A state, Ps, is a product state if it can be expressed as the tensor product of 2 other states, 1, Ps1, and 2, Ps2, each consisting of at least 1 qubit, if not or Ps, cannot be expressed in this form. It's entangled. For instance, 0, 1, or 1s, is a product state as it's 0, 1, 1, even 1, 2, 0, 0, plus 10. 2, 1, $100, prime $10, is a product state as you can factor 0. On the second qubit to get 1, 2, 0, plus 1, 0, 2, 1, Tiger 1, do. However, 1, 2, 0, 0 plus 11, 2, 1, 100 plus or 11 is entangled. Try as you might, you can't express it as a product of two 1 qubit states. Exercise 1.14 is 1, 3, 0, 0 plus 0, 1 plus 11, 3, 1, do nasa to 1, 11, entangled. What about 1, 2, 0, 0 plus 0, 1 plus 10 plus 5, 11, 2, 1, 100,000 plus so, 10, 11. When measured, entangled states exhibit correlations that defy classical explanation. Einstein called this phenomenon spooky action at a distance. Even if you measure one entangled qubit thousands of light years away from its partner, the results remain interconnected. 2. The no-cloning theorem, quantum copying prohibited. Get ready for a mind-bending theorem. Quantum systems typically refuse to be cloned, meaning we can't copy arbitrary quantum information. This property emerges due to the linearity of quantum gates. Imagine you want to copy a qubit using a 2-qubit gate U, 0, equal sign, UPI, peace. However, the no-cloning theorem asserts that this operation isn't possible in general. If such a U existed, a contradiction would arise, demonstrating the impossibility of quantum copying. 3. Controlled gates, expanding quantum operations. Controlled gates, your new quantum toolkit. You might wonder if controlled gates exist for various quantum operations. Yes, indeed. For any quantum gate U, a controlled U, CU gate, can be defined. Its action on the computational basis is C and 00 equal sign 00, CU and plus 30 hundreds, C 01 equal sign 01, CU1 R, CR size 10 equal sign R1 0, CU10, and so C10 11 equal sign bar 1 to 1 so CU11 1 U1. Constructing controlled gates is simpler than it appears. For instance, the controlled Z gate can be built using controlled X and two Hadamard H gates. Exercise 1.15. Check that the matrix of CCU is given by the matrix of U with an extra block structure. Prove the equivalence between controlled Z and controlled X with Hadamard gates. 4. Creating entangled states. Hello, quantum world. Time to create entanglement using controlled gates. Imagine you start with 2 qubits in the state 00, 100, and apply the Hadamard gate H on the first qubit. This takes you to 1, 2, 0, 0, plus 10, 2, 1, 100, plus 10. Then applying the CNOT gate, CX, yields the entangled state 1, 2, 0, 0, plus 11. 2, 1, $100, 11. Known as a Bell state. There are 4 Bell states, each with its distinct properties. Exercise 1.17. Prove that all 4 Bell states are entangled. Obtain circuits to create these states, using controlled X and controlled Z gates. In conclusion, congratulations, quantum adventurers. You've now explored the realms of entanglement, grasped the no-cloning theorem's implications, and mastered controlled gates. Quantum computing is truly a world of surprises, where classical intuitions crumble and new possibilities arise. With entanglement as a powerful tool, you're equipped to dive deeper into the world of quantum algorithms and applications, multi-qubit systems, quantum gates, and advanced algorithms. Welcome back, eager learners, to the next phase of our quantum adventure. In this continuation, we will delve even deeper into the fascinating world of multi-qubit systems, explore diverse quantum gates, and catch a glimpse of advanced quantum algorithms. Prepare to be awed and enlightened as we unravel the complexities of quantum computing. 1. Multi-qubit systems. Beyond the basics. Now that we've conquered the realm of 2-qubit systems, it's time to expand our horizons to multi-qubit systems. In the quantum realm, qubits exhibit entanglement and superposition, which become more intriguing as we add more qubits to the mix. A quantum state with n qubits requires 2 to n complex numbers to fully describe it, a stark contrast to classical bits. Working with multiple qubits and universality greetings, quantum enthusiasts, brace yourselves for a journey into the world of multi-qubit systems and universality. We've traversed the realm of 2-qubit systems, and now we're about to dive deep into the complexities of multi-qubit systems and the magic of universality in quantum computing. 1. 5.1 Multi-qubit systems. Let's start by extending our understanding of qubits to encompass multiple qubits, a cornerstone of quantum computing. 1. 5.3 Universal gates and quantum circuits. Universal gates in quantum computing are the building blocks that allow us to approximate any unitary operation using a reduced set of primitive gates. Applying quantum concepts to real systems greetings, fellow quantum enthusiasts. Now that you've familiarized yourselves with multi-qubit systems and universal gates, it's time to bridge the gap between theory and practice. Let's delve deeper into how we translate these quantum concepts into real-world quantum computations. Implementing quantum circuits. The transition from understanding quantum concepts to implementing them is where the rubber meets the road in quantum computing. Quantum circuits are at the heart of this implementation, serving as the canvas on which we paint quantum algorithms. Think of a quantum circuit as a sequence of quantum gates applied to qubits. Each gate represents an operation that transforms the state of a qubit. For instance, one-qubit gates like the RZ and RY rotations modify the probability amplitudes of the qubits, while the controlled NOT, C0 gate, establishes entanglement between qubits. Measurement and quantum state collapse. Measurement, a fundamental aspect of quantum computing, reveals the probabilistic nature of quantum systems. When we measure a qubit, we extract a classical outcome based on the probabilities associated with its quantum state. However, this measurement inherently alters the state of the qubit. For multi-qubit systems, the situation is more intricate. Measuring a single qubit can affect the state of entangled qubits. In such cases, the resulting state after measurement can be expressed as a combination of states that comply with the measurement outcome. This phenomenon, known as quantum state collapse, underscores the intricate interconnectedness of quantum information. The quest for universality. One of the most captivating aspects of quantum computing is its pursuit of universality. While classical computers employ a fixed set of logic gates, quantum computers aim for a more versatile set that can approximate any unitary transformation. This set, often composed of one-qubit gates and the Kaicenat gate, empowers quantum computers to emulate classical logic and perform complex operations on quantum states. This universality is akin to the Turing completeness of classical computers, which can emulate any other classical computer. In the quantum realm, universality underscores the richness of quantum operations and their potential to revolutionize computation. Implementing quantum circuits in practice. As we step into the realm of practical implementation, envision working with quantum programming languages or platforms. Quantum programming languages, like Qiskit and Cirq, offer the means to define quantum circuits, simulate their behavior, and even execute them on real quantum devices. Quantum simulators play a pivotal role in this journey. They enable us to simulate quantum circuits on classical computers, providing insights into how quantum systems evolve over time. This simulation stage serves as a vital testing ground for refining algorithms before attempting them on actual quantum hardware. In conclusion, quantum enthusiasts, you've traversed the fascinating landscape from abstract theory to tangible implementation. You've glimpsed the power of quantum circuits, grappled with the nuances of measurement and state collapse, and marveled at the quest for universality in quantum gates. With a foundation in place, we're poised to embark on the next leg of our journey, applying quantum computing to real-world problems. We're on the cusp of witnessing quantum algorithms in action, and the practical applications that emerge from this revolutionary field are bound to reshape the way we approach computation and problem-solving. N-qubit systems, any unitary operation, can be constructed using one-qubit gates and the Kaicenat gate. The Toffoli gate, which acts as a controlled NOT gate, is an example of a gate that cannot be constructed solely from one-qubit and Kaicenat gates. The Toffoli gate is particularly interesting because, when combined with ancillary qubits, it enables the simulation of any classical Boolean operator. This universality allows us to transform classical digital circuits into reversible quantum circuits by employing a classical version of the Toffoli gate. The tools of the trade in quantum computing. Welcome to the fascinating world of quantum computing tools. As we embark on this journey, we'll explore the range of software frameworks and platforms that empower us to harness the power of quantum algorithms. In this chapter, we'll delve into the key tools, including Qiskit and PennyLane, that allow us to implement quantum circuits and run them on simulators or real quantum hardware. 2.1 Tools for Quantum Computing, an overview. Imagine a world where we have quantum chips right in our laptops, but we're not quite there yet. However, we do have some real quantum computers at our disposal, albeit with limitations. Additionally, our trusty classical computers can effectively simulate quantum processes, particularly for a limited number of qubits. In this chapter, we'll uncover the tools that bridge the gap between quantum theory and practical quantum computing. 1.1 Exploring Quantum Frameworks. Before we dive into the specific tools, let's take a quick look at the quantum software landscape. While Qiskit and PennyLane are our primary focus, it's worth mentioning some other noteworthy frameworks. Quark. This simulator stands out with its graphical user interface that lets you design quantum circuits via drag and drop. It's a fantastic platform for demonstrations and quick prototyping. Q-Hash and Microsoft's QDK. Q-Hash is a dedicated programming language tailored for quantum computing. It's part of Microsoft's Quantum Development Kit, QDK, equipped with simulators and a connection to Azure Quantum for real quantum hardware execution. Quest, the Quantum Exact Simulation Toolkit, Quest, is designed for optimal performance. It's written in C++ and offers an avenue for hardware-intensive simulations with a focus on large qubit systems. Cirq, developed by Google, Cirq is a Python-based quantum framework suitable for algorithm design, simulation on classical devices, and execution on real quantum hardware. It's also integrated with TensorFlow Quantum for quantum machine learning. Qiskit, IBM's flagship quantum framework, relies on Python and boasts a rich collection of simulators. It enables the submission of algorithms to IBM's actual quantum hardware. Qiskit provides a comprehensive library of quantum circuits and algorithms, which we'll delve into more deeply. PennyLane. This newcomer, developed by Xanadu, targets quantum machine learning while serving as a versatile general-purpose quantum framework. It leverages Python as its host language and stands out for its interoperability with other classical machine learning frameworks. 2.2. Working with Qiskit. Let's focus our attention on Qiskit, the robust quantum framework from IBM. With Python as its foundation, Qiskit offers an array of simulators and direct access to real quantum devices hosted by IBM. It's not just about running quantum algorithms. Qiskit is an expansive ecosystem that covers various aspects of quantum computing. 2.3. Working with PennyLane. PennyLane, developed by Xanadu, caters specifically to quantum machine learning, though it's equally adept at general quantum computing. Like Qiskit, PennyLane embraces Python, but what sets it apart is its exceptional interoperability. Through various plugins, you can export PennyLane circuits to other frameworks and harness their unique features. Conclusion. As we conclude this exploration of quantum computing tools, remember that the landscape is vast and rapidly evolving. Qiskit and PennyLane are our main allies, offering us the means to implement, simulate, and execute quantum algorithms. Navigating the quantum landscape. Now that we've introduced the primary tools, Qiskit and PennyLane, let's take a closer look at their individual features, capabilities, and how they can be leveraged for various quantum tasks. 2. 4.1 Qiskit, the IBM Quantum Framework. Qiskit, developed by IBM, is a versatile and comprehensive quantum framework that empowers researchers and developers to engage with quantum computing. It's built on Python, a popular programming language, making it accessible to a wide audience. Simulators and quantum hardware access. Qiskit provides a range of simulators for emulating quantum behavior, enabling algorithm development and testing. Moreover, it offers direct access to real quantum hardware through IBM's Quantum Experience, allowing users to run their algorithms on actual quantum processors. Quantum circuits and gates. One of the core aspects of Qiskit is its quantum circuit representation. It allows users to construct quantum circuits using a user-friendly syntax and visualize them. The platform supports a wide array of quantum gates that can be combined to create complex operations. Quantum algorithms and libraries. Qiskit includes a library of quantum algorithms, covering a spectrum of applications including optimization, cryptography, and machine learning. Users can access pre-implemented algorithms or customize their own. Qiskit, PennyLane, and Ocean welcome students to our exploration of the quantum software landscape and the tools at our disposal for quantum computing. Today, we'll delve into the reasons behind our choice of Qiskit, PennyLane, and Ocean as the main frameworks for our journey into quantum algorithms and applications. Why Qiskit, PennyLane, and Ocean? As you've just learned, the quantum computing software realm is rich and diverse. However, we've selected Qiskit, PennyLane, and Ocean for specific reasons that align with our learning goals. Qiskit, the quantum powerhouse. Qiskit, developed by IBM, stands out due to its extensive built-in algorithms, functionalities, and a robust user community. Its comprehensive nature makes it a dominant player in the quantum software landscape. Not only does Qiskit provide a wide array of algorithms, but it's also well supported by various quantum hardware providers, making it a universal language of quantum computing. PennyLane, quantum machine learning pioneer. PennyLane, developed by Xanadu, might not be as widely adopted as Qiskit, but it shines brightly in the realm of quantum machine learning. Its smooth operation, impeccable documentation, and unparalleled interoperability with quantum and machine learning frameworks set it apart. PennyLane's ability to compute gradients of quantum circuits enables quantum optimization tasks, opening the door to innovative applications. Ocean, Bridging the Gap to Quantum Annealers Ocean, a unique software package, brings quantum annealers into our toolkit. It's a remarkable choice for those interested in working with quantum annealing hardware, enabling the definition and execution of problems on real quantum hardware. Ocean also simplifies the process of learning, especially for problems related to natural sciences, finance, and more. Why not others? While frameworks like Q-Hash and Cirq are excellent choices, Qiskit and Penny Lane's strengths in quantum machine learning and quantum optimization are hard to beat. Quest's performance is noteworthy, but it lacks user-friendliness and essential features for our focus. Keep in mind, the simulation performance of Qiskit and Penny Lane is more than sufficient for our purposes. Introducing Qiskit. Now that we've understood our framework choices, let's delve into Qiskit in more detail. Working with Qiskit. In this section, we'll embark on the journey of using the Qiskit framework. We'll explore its structure, learn how to create quantum circuits, implement quantum gates, and perform measurements. The components of Qiskit. Qiskit is a comprehensive framework with distinct components, each serving a vital role. Qiskit Terra. At the heart of Qiskit lies Terra, responsible for quantum circuit handling and construction tools. It features a basic Python-based simulator called Basic Air, and it can interface with IBM's quantum provider to execute circuits on real quantum hardware. Qiskit Air, built on Terra. Qiskit Air provides high-performance quantum simulators written in C++, optimized to efficiently utilize hardware resources. Qiskit Machine Learning. Tailored for quantum machine learning, this component houses various algorithms suitable for NISQ devices. It offers seamless integration with PyTorch for training quantum machine learning models. Qiskit Optimization. Focused on quantum optimization algorithms, this part becomes vital in part 2 of our journey. Qiskit Nature and Finance. For applications in quantum physics, chemistry, and finance, Qiskit Nature and Finance offer algorithms for specific problems. Qiskit Experiments. Designed for noisy quantum computers, it facilitates characterization, benchmarking, and calibration of quantum devices. Qiskit Metal and Dynamics. The latest additions, Metal enables quantum device design, while Dynamics supports modeling of quantum systems. Constructing quantum circuits in Qiskit. In Qiskit, quantum circuits are quantum circuit objects. You can initialize these objects with a specific number of qubits and classical bits. Quantum gates are added using methods on the circuit object. Gates like X, Y, Z, Hadamard, and rotation gates can be applied sequentially using the circuit's methods. Qiskit also provides control over quantum and classical registers, allowing flexible circuit design. Measurement operators in Qiskit. Measurement is a crucial aspect of quantum circuits. You can measure specific qubits and store the results on classical bits using the measure, qubits, bits method. For measuring all qubits and storing results on corresponding bits, use measure_all. Qiskit effortlessly handles these operations, enabling efficient measurements in your quantum circuits. In our next session, we'll continue our exploration of Qiskit by diving into quantum gates, measurements, and hands-on exercises. So stay tuned as we unlock the power of quantum computing through these incredible tools. Introduction to Qiskit Air. In the world of quantum computing, simulation plays a crucial role in understanding and developing quantum algorithms. Qiskit, a popular quantum computing framework, offers the Air package for simulation purposes. Air provides powerful simulators that allow us to study and analyze quantum circuits before running them on actual quantum hardware. Importing necessary modules. To start using Qiskit Air, we need to import the required modules. Python copy code from Qiskit. Providers, AR import, Air simulator. Creating an Air simulator object. We can create an Air simulator object in 2 different ways, depending on whether we want to utilize a GPU for simulation. Python, copy code sim, =Air simulator. Hash standard simulator without GPU sim, _GPU =Air simulator, device GPU. Hash, GPU powered simulator. Keep in mind that using a GPU for simulations is beneficial for resource-intensive tasks, but it might lead to worse performance for less demanding simulations due to communication overhead. Simulating quantum circuits. When simulating quantum circuits, we often perform multiple measurements to account for probabilistic outcomes. To simulate n shots of a circuit QC, we use the execute function, Python copy code job =execute QC sim shots =n shots, result =job result, counts =result, get counts. The get_counts method provides a dictionary of absolute frequencies of each outcome. Example, simulating a simple circuit. Let's illustrate this with an example. Consider a 2-qubit circuit with a Hadamard gate on the first qubit, followed by measurements on both qubits. Python copy code QC =, quantum circuit 2, QCH 0, QC measure, range 2, job =, execute, QC sim, shots =, 1024. Result =, job, result counts =, result, get counts, print in counts. Visualization. Visualizing results can enhance our understanding. Qiskit provides tools for this, such as plot_histogram, Python copy code from Qiskit, visualization import * plot histogram counts, accessing state vectors. Besides measuring outcomes, we can access the quantum state vector using QC, save state vector, and result, get state vector, Python copy code QC, save state vector, result =, execute, QC, sim, shots =, 1024. Result, SV =, result, get state vector, print SV, running on real quantum hardware. IBM Quantum offers access to real quantum computers. After setting up your IBM ID account and obtaining an API token, you can run circuits on these devices. Python, copy code provider = IBM Q load account, dev_list = provider, backends filters lambda x configuration, and qubits, = 5, simulator = false, dev = least_busy, dev_list, job = execute, QC dev, shots = 1024, job monitor job, result = job result, counts_dev = result, get counts, comparing simulation and real hardware results. By comparing simulation results with those from real hardware, we gain insights into the impact of noise on actual quantum devices. Conclusion. With Qiskit Air, we can simulate quantum circuits, analyze outcomes, and prepare ourselves for running experiments on real quantum hardware. This foundation is essential for further exploring quantum computing concepts and applications.